talking about Hess's law, okay? And so there are two forms of Hess's law that we'll talk about. And his basic idea was that you could have many steps to a reaction and figure out the energy changes for those steps, and you could add them up to equal the total, okay? And so sometimes there are reactions that you can't you can't actually react it in a lab, and we want to know how much energy is associated with it. But if you can find out what the many steps are, they call them intermediates, then you can add those up and you can manipulate these reactions. We're not going to end up doing manipulation today. What we are going to do is we're going to calculate what the energy is for a reaction as it's written. Okay, and we're going to use what is called the chart of thermochemical values. So we'll look at those a little bit later. So it says, whose law is this? It's called Hess's law, and then thermochemical equations. So an equation that includes an energy like delta H is called a thermochemical equation. And delta H is the enthalpy change, or it's just the change in what? Heat or energy. Perfect. So enthalpy is the blank evolved or absorbed in a reaction. It's simply the heat that is evolved or that's absorbed inside of a reaction. The location of the energy term indicates whether the change is endo or exo. Okay? And so if the energy is located on the reactant side of the equation, things that are on the reactant side are coming into the reaction. So imagine putting it into the beaker or putting it into the flask. If it's on the reactant side, then that means that energy is being endothermic. It's absorbed. Very good. It's absorbed or gained. Okay? And the change then, we would say, is endothermic. Anybody remember, would delta H be positive or negative if it's being gained? Then it's positive if it's being gained. Okay? If the term is on the product side, then that means that energy is released. And so in this case, your delta H would be lost, so that would be negative, and the change is exothermic. Usually, it's not written inside of the equation, but it's written to the right of the equation, and so that's where we'll use the delta H signs, okay? So delta H being positive, again, we said the reaction is positive, is everybody? For the fifth, sixth time maybe? Endo, awesome. And so if it's endothermic, then we say that energy is being absorbed or gained. Perfect. And then again here, if it's negative, then the reaction is exo, and then the energy is released or lost. Perfect. Okay, so make sure that you have this down, all right? That's going to be one major thing that you'll see over and over again. And if you don't have this down, that it's negative is exothermic, means that it's released, okay? And energy would be leaving on your product side. So maybe a gas is coming off, whatever your product is, then energy might be released. If it gets hotter, your reaction gets hotter, then that means it's exothermic too, okay? So what is enthalpy? It's simply the energy change. So it's the amount of what? The amount of what? I heard it. Heat, awesome. Or energy. Absorbed or released for a reaction. And I'm going to write reaction as RXN. And guess what the symbol is, everybody? Yep, delta H. Awesome. Delta H. Okay, so that's enthalpy. So a thermochemical equation is an equation that includes the standard enthalpy change. So it says, consider this example. We have hydrogen gas and oxygen gas creating water, okay? And then it puts this plus 242 kilojoules in there, okay? Which doesn't look like any chemical symbol that you've seen before. So this is representing what? Delta H. Very nice, okay? So here it says H2 plus 1/2 O2 yields H2O. All of this is the same, but now you can also write it where you take delta H out. And instead of putting it on your product side, you could say that you could just give delta H a value. Well, we know the number is what? 242 kilojoules, but the question is it positive or is it negative? Well, if energy was being released and it's on your product side, if it's being given off and it's being released, then the sign of your delta H should be what? Negative. Okay? So if it's on your product side, it's negative. If it's on your reactant side, the energy value, then it's going to be positive. Okay, so negative on the right and positive on the left. So let's try Hess's law. So it says, over the years, scientists have devised a chart that's very helpful when dealing with energy of a reaction, And it's called the thermodynamic quantities for selected substances at 298.15 Kelvin. Please refer to your copy now. So let's take a look at the copy. And it says, what's important to us at this time are the HF values. They're called the standard heats of formation. So we're going to look at those in just a second. So we're looking at the delta H's. What this is, well, we'll talk about this in a second. So take a look at your chart for a minute here. And what this is giving us is it's giving us the amount of energy associated with these different substances, okay? And you can see every once in a while you get a value of 0. And I want you to pay attention to those zeros for a minute, okay? So where do you see the very first 0? And we're just looking at the delta H values. This is called Gibbs free energy. It's the amount of energy that basically is that you have available after a reaction has taken place. That's called Gibbs free energy. This is entropy. Anybody remember what entropy tells you? Disorder. Awesome. How much disorder a system has. So like a gas is more disordered than a solid. So if your reaction tends to go more toward creating gases, it's becoming more disordered. So we're not looking at either one of these. We're only looking at the delta H. Okay? We're just going to look at delta H. So where's your first 0? Aluminum solid. Okay, where's your second 0? Barium solid. Let's keep going. Your third one? Beryllium solid. Where's your next one? Bromine. But there are a whole bunch of bromines. Which bromine? Liquid. Why? Why is this one 0, but bromine gas, Br2 gas, and Br minus, and the other Br gas are not 0? What do you think these zeros are representing? Let's keep going. What about this next one? Where do you see a 0? Calcium in what form? Solid. What about the next one? Carbon in what form? Solid in the graphite form. What do you think?
Is this like how it is on the periodic table?
Yes, it is. Awesome. Perfect. Okay. The way it exists in nature, remember on the periodic table, the phase that they have, black means solid, blue means liquid, red means gas. Okay. The way that it exists on the periodic table, that's in its most stable form, the way that it exists on Earth at room temperature, at 25 degrees Celsius, or what they're calling here, 298.15 or 25 degrees Celsius. So that's what they're using as the 0 values, okay? So that means that it is as it is in nature. There's no energy released and there's no energy absorbed to form it. That's how it exists on Earth, okay? So that's what those zeros are representing. So if you keep looking, like look at chlorine, which chlorine is 0?
CO2.
CO2, which CO2? Gas. That is the only one that's there, okay? Whereas something like cobalt, if you take a look at cobalt on the periodic table number 27, that's black. And black means what? Solid, okay? So cobalt would be a solid in its natural state, all right? How is this arranged? How is the table arranged? Is it arranged in increasing numbers? How is it arranged? Alphabetically. Perfect. I want to show you there's an exception. So it's alphabetical. You can see it goes from aluminum, then to cesium, then to chlorine. Flip your page. Then it goes hydrogen, and it keeps on going to sodium, and then it ends at zinc, okay, in really small numbers. I want you to take a look and find water, because where do you think water would be? Under hydrogen. Take a look under hydrogen. Do you see water there? No. Where's water? Under oxygen. Okay, so water is actually under the oxygen, so that's the one that I just wanted to make sure that you saw, because a lot of times people are like, I can't find water. Water's not on there. It's not on the chart. It is, it's just under oxygen. Okay? Same thing with, like, if you get an acid, for example, something that starts with an H, there's only hydrogen under the H section. So if you get like nitric acid, for example, you want to look under the nitrogen section instead. And then you'll find like HNO3, HNO2 is there. So if it's something like an acid and it starts with an H, look under the other element. Okay? Does that make sense? Okay, so we're just going to take the values off of this chart, and then I'll show you what we're going to do with those values. Okay. So, so it says the standard heat of formation is the energy associated with forming 1 mole of that chemical from its elements in their standard states. From its elements in their standard states. So what this number is telling us is, what did it take to make this substance from its own elements. Like if you had NaCl, what elements is NaCl salt made of? Sodium and chlorine. But in its natural state, it would have to be sodium is black, which means it's what? A solid, and chlorine is red, which means it would be a gas. What else do you know about chlorine? It's diatomic. Awesome. So it wouldn't be Cl gas, it would be Cl2 gas. And when we say elements in their natural states, that means that it has a 0 value as its thermochemical value. Okay? So it says the energy values are assigned in the units of, take a look at your chart. What does that, that Thermo chart, what are the units of delta HF?
Kilojoules per mole.
Perfect, kilojoules per mole. Not all chemicals appear on the chart, but it's very useful for calculating the energy of a reaction if the chemicals are listed. So Hess's law states, so I want to make sure that you understand this real quick before we move on. So we use the calorimeter, and we can figure out the amount of energy, the delta H, just by doing an equation using, what is that equation? What do we call it? What's that equation that we were using to do the Everybody. MCAT. Awesome. So we can use the MCAT equation, and we can figure out what delta H is equal to. Okay? And so what you basically do is we took a calorimeter, we put water inside the calorimeter that we knew the mass of, we threw a thermometer in there, and we waited to see how the temperature of the water changed. Okay? Did it change a lot? Yes or no?
No.
No. Only by like 1 or 2 degrees, right? So it barely changed. The water temperature barely changed. Some of you may have gotten a 3-degree difference. That's a big difference for water, okay, in this case. So what we ended up doing was we took the mass of the water that we had, the specific heat of the water, which we know is that value, that 4.184. You could use it in calories or joules or kilojoules, whichever one you want. And then what's the only other thing you have to multiply by? The mass, the specific heat, and the temperature change. Awesome. Where do you get the temperature change from? Yep. What was your initial temperature of your water inside of here? What's the final temperature of the water after you've added the metal into there? Okay, and we can calculate the delta H. We don't want to keep doing that every single time. So that's where this chart comes in. Instead, we can just subtract. We can use a chemical equation, and then we can find out what the value is using the chart, the Thermo chart. Okay? So calorimetry would be one way of doing it, and then another way would be using the chart. So Hess's law states the enthalpy change for any reaction is the sum of the standard molar enthalpies of the products minus the reactants. Okay, so you're going to do, just like anytime that you do accounting, you want to know your final minus your initial to figure out how much you have your net, what your net gain is. So the relationship is expressed in the following equation with a symbol, this is called sigma, and that means the sum. Okay, so this one means what? Sum of the products minus the sum of the reactants. Okay, you could do it this way. You could sum both of them and then subtract them. I find it easier to just add my products together and subtract both reactants. You can do it either way, and I'll show you both ways. Okay. So it says if you're given a chemical equation that shows compounds in their states, you can look up the standard molar enthalpies of formation for the substances and use them to find your delta H. So here's one thing we need to know before we do these problems, and they're really, really easy. Free elements. We already talked about them. They're the ones that have a value of 0, where their delta H is equal to 0. So it says metals in what state typically?
Solid.
Solid. Awesome. Except mercury. Mercury is in liquid. Very good. The diatomics. Look at hydrogen. What would hydrogen be? Gas. Nitrogen? Gas. Oxygen? Gas. Fluorine? Chlorine? Bromine? Liquid. Awesome. Iodine is black. Solid. Okay? The remainder of the monatomic elements in their natural state are free elements, and then these are just some special elements. We had said the carbon in the solid graphite form. P4 gas is also 0, S is 0, S solid is 0 sulfur in the solid state. You will always get the chart, okay? You're going to have the chart to use, so you don't have to worry about memorizing anything. I would know, like, the 0 ones, but you're going to have your chart anyway, okay? All right? So let's try it. So step 1 just says to use a reference table, and step 2 says just apply Hess's law and go products minus reactants. One thing that I'm going to tell you to do is circle the coefficients so you don't forget to include them. Because if you have 2 salts, 2 NaCl's, you have to multiply your NaCl value by 2, okay? So that's the only thing is you have to take your coefficients into account. So let's try it. First thing we're going to do is, and totally up to you how you want to do this, okay? But I'm going to tell you that people make a lot of mistakes on these problems, and you're less likely to make a mistake if you follow a set way of doing these, okay? So let's start off with the SO2. So I'm going to ask someone to look up the SO2. Let's just start in this corner here, and then we'll just kind of work our way back. So if you can look at your chart, and I want you to find SO2 on the chart. And we know that it starts with sulfur, so it's going to be on the back of the page. So see if you can find sulfur. And once you find it, you're looking for the gas version of it. And do you have a number? Negative 296.9. Is that what it says?
Yeah.
Okay, awesome. I can't see it on here. So it's this one right here, but I'm having trouble. So negative 296.9. Awesome. Okay, so let's go back to this. Negative, and so it's 2 times negative 296.9. Okay, I'm just going to do a dot for my multiplication sign here. So 2 times negative 296.9. Okay, next person. Oxygen, and you may not have to even look at oxygen. 0. Awesome. Even if there were 3 or 4 or 5 of them, it's still 0 times whatever number, which is just going to give you 0. So we can do 0 for that one. Okay, the next one is SO3, which will be right next to SO2, or right under or above it.
395.2.
Awesome, negative 395.2. And again, don't forget to multiply by 2. Okay? So here's what you're going to do in your calculator. Okay? You need to do products. It's sum of the products minus the sum of the reactants. Okay? So where are the products? On the right or on the left? On the right. So don't forget RAP, because that will mess you up and you'll get all of your answers wrong. Okay? Reactants, arrow, products. All right? So products are on the right. So you're going to do this one minus this one. So go ahead and plug that into your calculator and tell me what you get. Negative 196 point something. Here, let me grab it here too to make sure that's right. Yeah, negative 196.6? Okay. So what you're doing, everyone try this. Okay, so what you're doing in your calculator, I would do this. I would do parentheses 2 times negative 395.2 minus parentheses 2 times negative 296.9. Since that's the only product and that's the only reactant, we only have to subtract the 1. Okay, and it's negative 196.6 kilojoules will be the answer. Good? If you didn't get it, make sure that you talk to someone sitting around you too. Okay? All right, let's try the next one. So now we'll do it in 2 different ways because I want you to see. And if you can get one of them, this is the hardest one that it really gets. This is the hardest that it gets. So if you can get this one, then you're good to go, okay? And so we're pretty much all set with it. All right, so let's get our values down. So now I'm back to the 4th person in this row here. Okay, so if you can find KClO3, which K is not, doesn't start with a K. What is that? Potassium. So look under the potassium section and see if you can find the value for KClO3. Negative 391.2. There's only one of them. Okay, so we're good. We don't have to do that. This one here, so I'm going to right away, you can even do this right away if you have a coefficient. Just write it down there so you don't forget to multiply by that. Okay, next person, PCl3. So P is phosphorus.
Negative 319.
Awesome. Negative 319.6. Okay, then we're up to the front here. This POCl3.
Negative 597.
Awesome. Negative 597.0. And KCl solid, please.
Negative 435.9.
Negative 435.9. Okay. I want to make sure you do your order of operations correctly. Okay? It's these minus these. There are 2 ways to do it. Okay? you can either multiply this, add these together, and write your answer down for that. Some people think it's a lot easier doing it this way, so I'm going to show you this way of doing it. Some people write this, and then they just do this plus this, minus, minus, done. This is all you have to show me. Okay? This is all you have to show me as far as work goes. But you want to be careful with getting your calculation wrong. With making sure that you calculate. Okay, so I've got negative 391.2 plus parentheses 3 times negative 319.6, and that gives me negative 1350. Then this one is 3 times, this is the slower way to do it, by the way, negative 597 plus negative 435.9. So, but again, some people like it this way. So, oops. Is it negative, did anybody do this one already? Negative 2226.9? Yeah, mine went into fraction mode. 2226.9. Once you have that, now you want to do products minus reactants, which means you have to do this number minus that number. So that number, my answer, minus negative 1350. And I got negative 876.9.
Yeah.
Delta H is equal to negative 876.9 kilojoules. Okay? The other way to do it would be, again, take this number, add this number, subtract both reactants. Try it, okay? You have to subtract though, because both reactants need to be subtracted. Otherwise, you're adding these together, okay? Otherwise, you're going to add them together to get those answers. So I did, I showed you how to do it that way. I think it's a lot faster to just plug it right into your calculator, yes? Yeah.
How do you know when you're done kilojoules?
So each one of these are kilojoules per mole that we got from the chart.
Okay.
But when you say per mole, it's per mole of what? Like it is per 1 mole for this reaction. It is for 1 mole of this, but it's for 3 moles of that. Remember, the coefficients represent the moles. So that's why we just leave it as kilojoules unless they're telling us per mole of something. Okay? All right, good? Okay, so it says, let's see. That's basically it. Yeah, that's basically it. I do want to show you what happens when you like reverse a reaction. So let's just do that last part. It says, assume you need to find the energy of a reaction. It's impossible to measure the energy change through calorimetry or any other reasonable means. If you know the enthalpies of some reactions, you can manipulate the equation so they add up to the targeted equation. Then again, you would sum them up to find the original reaction's enthalpy value. The idea is that the enthalpy changes for reactions can be added together to give the enthalpy change for an overall reaction. This is also called whose law? Hess's law. It's called Hess's law. Hess's law states the overall enthalpy change for a reaction is equal to the sum of all of the intermediate steps added together. Okay, so which is the sum of them? So the sum of all the elementary reactions. The sum of all of the elementary reactions. And it says, this means if the intermediate reactions are known, the enthalpies of each intermediate reaction can be what together? Added. Awesome. They can be added together to find the enthalpy of the target. And then it says to apply Hess's law, you may have to perform 1 or 2 simple manipulations involved. One type of manipulation is multiplying or dividing an equation by a factor, and the other one's reversing it. When a reaction is reversed, guess what the only thing is that changes? Yep, the sign. Positive or negative. Okay? So it says calculate the enthalpy change delta H for 1 mole of sodium chloride shown here. All right, so let's do our enthalpy change for this. So we got back to the second to the third person. So if you can find sodium solid, or maybe you don't have to look at the chart, what would sodium solid be? 0. Awesome. It's in its standard state. Next person. What about Cl2 gas? And it's very possible that you don't have to look at that either. 0. Also, it's in its natural state. So next person, if you can tell us it's sodium chloride. So you're looking under the sodium section. Okay, negative 410.
I didn't
Oh.
actually check.
Okay, negative 410, yeah. And I think I may have, the value may be a little bit different. Negative 410.9, okay. So what you're doing here is typically you would do 2 times this, okay? And so I think it is a little bit off on there. It should be, the value should be a little bit off. It should be exactly the same. You would have to multiply these two to get that answer, okay? And then it's minus 0, minus 0. This one says to write the reverse form of this reaction. What would the reverse form of the reaction be? Well, if we flipped it and we did NaCl solid, then arrow, Na solid plus 1/2 Cl2 gas, what's the only thing that would happen to this value of delta H? It would be exactly the same except?
Positive.
Positive. Very nice. The only difference is it would be a positive 411.2 kilojoules. Okay? That's the only difference with it. Some references may have different values, so I think that's why they're slightly. Okay, and